Okay, I think we are ready to start now. Hello, everyone, and welcome to this new edition of the course on processing in memory. The official title of this course, as you can see on the screen, is Data-Centric Architectures, Fundamentally Improving Performance and Energy. Today is March 9th, 2023, and we are right now starting the Spring 2023 edition of this Processing in Memory course. You can find information about this course in the course catalog at the ETH website. And here you can find some learning material and some more information about the course, and also a description of what's the main objective of this course. And I think it's always good to start reviewing what's this main objective. One important key bottleneck in computing systems these days is the data movement that is all the time needed between the memory units and the compute units. And this data movement dominates performance and dominates the energy consumption. In some recent study, we observed that 62% of the total system energy in consumer applications is spent on the data movement. This is what it's called the data movement bottleneck. And this affects every sort of modern workloads, from machine learning, computational biology, graph processing, databases, etc. In order to solve this or to deal with this data movement bottleneck and to alleviate this data movement bottleneck, it's necessary to do a paradigm shift. This paradigm shift consists in making compute systems more data-centric or more memory-centric. And a way of doing so is placing compute capability or some sort of processing elements closer to the memory, to where the data resides, or even inside the memory itself. As I said, the data movement bottleneck is really harmful in current computing systems, and we can see this slide, which is not so recent anymore because it's from 2015 from Bill Daly, where we can clearly observe the important difference or the huge difference in energy consumption of memory accesses and computation. As you can see, one access to DRAM can be around 16 nanojoules, while computing a 64-bit double precision addition, for example, might take only 20 picojoules. So basically, 3 orders of magnitude, something between 2 and 3 orders of magnitude, more energy consumption for memory accesses than complex operations like a floating point or double precision floating point addition. So these are the issues that we are going to tackle and try to alleviate in this course. And that's the, let's say, key goal of this P&S course, on this projects and seminar course on processing in memory. Let's very briefly review what are contents and objectives of this course. As we are doing right now, we are going to introduce in this course the data movement bottleneck, which is a major threat to high performance and energy efficiency of current computing systems. We are going to study workloads and what are key workload characteristics that they make them more prone to the data movement bottleneck. And we are going to review traditional approaches to alleviate the data movement bottleneck. And at the same time, get familiar with new approaches to dealing with this data movement bottleneck. Processing in memory solutions is how we call them. We are going to work hands-on because this project and seminar course is a hands-on course. And the way that you will work is, you will see, we will present in an upcoming meeting, we will present the different projects that we are going to offer you. But basically, things that you will likely do is analyzing real workloads, programming PIM architectures, simulating new PIM proposals, etc. PIM, even though this course is relatively new, is not a new paradigm at all. It's already more than 50 years old. And this paper that you can see on the screen is the oldest that we are aware of, this cellular logic in memory arrays from William Kautz, published in 1969. 1 year later, this logic in memory computing from Harold Stone. So as you can see, processing in memory is an old idea. But even though it's an old idea, and as we will probably discuss later in this course, it has not become a reality until now. Back in 2019, ABMEM, which is a French startup, presented their processing in memory system, which is the first real world and commercially available processing in memory system that we are aware of. It's called processing in DRAM because the memory itself is DRAM memory subarrays, but near each of these memory arrays, there are small processors called DRAM processing units or DPUs. We are going to talk about this system with a lot of detail in this course with several lectures because we have worked extensively with this system in the last couple of years, have published several papers and have analyzed and understood what are suitable workloads for this type of processing in memory system. Here you can see a picture of this processing memory system with 2560 DPUs or PIM cores, PIM processing elements, or processing elements near the memory arrays. And here in this entire system, you can identify the dual socket CPU host. And then there are some DRAM DIMMs because the PIM enabled DIMMs in this system coexist with conventional DRAM DIMMs that keep working as main memory of the host. And then we can find a bunch of these PIM enabled memory DIMMs that are the ABMEM DIMMs that contain these small processors called DPUs. As I said, have been working on this system for a couple of years already. This is some news from ETH. This was actually published last year, talking about our recent work. Yeah, you can click on the link and check this interesting piece of news. But if you want to get the deep dive into the ABMEM PIM system, you just need to wait for the next upcoming lectures. But in the meantime, if you're curious, you can already take a look at one of our papers. This was the first one where we did the initial analysis of this architecture, understanding its microarchitecture, its instruction set, and also understanding what workloads are suitable for this PIM system. This is the abstract of the longer version. We also published a shorter version of this work, and we have delivered several talks about this topic. This is one of them. This was a Safari Live seminar in July 2021, very long seminar explaining all the details of our work. I'm talking about the ABMEM PIM system, but ABMEM is not the only company that is working on creating processing in memory systems. And in 2021, exactly 2 years ago, Samsung announced their first processing in memory system, PIM architecture targeted at AI and machine learning applications. We are going to talk in one lecture about this function in memory DRAM or FIM DRAM, or also called HBM PIM, because it's based on HBM memory, as you can see on this slide. And let me give you a very brief introduction about it. HBM memory is a 3D stack memory. So what that means is that we stack multiple layers of DRAM on top of each other in order to be able to provide higher memory bandwidth. And that's why this HBM memory exactly means high bandwidth memory. And what Samsung did was modifying some of these layers of DRAM in order to integrate small processing units called PCUs. Here in this photo, you can see the cell array banks. So the bank 0 and bank 1, or here we see bank 2 and bank 3. And you can see how in between two memory banks, there is one of these PCU blocks. This PCU block, as we will see in the corresponding lecture, is a small SIMD unit with 16 lanes that can operate on 16-bit floating point values. And basically, main operations that it can perform or can execute are multiplication and addition. as we are going to discuss probably several times in this course, multiply and accumulate are key operations for machine learning and artificial intelligence. And that's why this Samsung SIMDRAM is basically focused on that sort of operations. Another proposal from Samsung that was presented a few months later is the Samsung AX-TIM. As you can see, this one is different. It's not based on HBM memory. It's based on DDR memories. And the basic idea is that on each of the DIMMs of DDR-X memory, it's possible to place, probably inside this AX-TIM buffer that you can see, it's possible to place some small FPGA, some small reconfigurable fabric, and implement and synthesize some compute elements, processing elements inside these small FPGA. In their first paper, Samsung tested this AX-TIM system for recommendation systems. Later, I've seen some more recent publication for databases. We'll probably talk about it as well in the corresponding lecture, because we will have a lecture about this Samsung AX-TIM. And more recently, actually last year in February 2022, it was another major DRAM vendor, SK Hynix, that they announced their own processing in memory system, in this case called Accelerator in Memory, or AIM. Same as the Samsung HBM PIM or FINDRAM system or FINDRAM architecture, this AIM from SK Hynix is also targeted at machine learning. And because of that, it has relatively similar structure and organization. So as you see, placing processing units or process units near each of the memory banks. Key difference is that instead of using HBM memory, here the memory is GDDR6. And well, it's also, I mean, these processing units are slightly different from the ones in Samsung, but also specialized for multiply and accumulate operations, as you can see here in this table. So this is just a very brief introduction to the existing processing in memory architectures that, as I said, we are going to cover with a lot of detail in this course. But now I would like to continue introducing the course itself and talking about what are going to be the goals and key takeaways of this work. So this PNS course is aimed at improving your knowledge in computer architecture and in processing in memory, technical skills, improving your technical skills in parallel programming, because you are going to have the opportunity to program a real processing in memory system, and also improve or making you familiar with computer architecture simulation. This course is also a good opportunity to improve your critical thinking and analysis. You're going to have the opportunity to interact with the Safari research group, as you will see, or as I will show you in a couple of slides. Is a very large research group, working on many different topics in computer architecture, systems, applications such as bioinformatics, and you are going to have a very tight and direct supervision from researchers in our research group. And you are going to get familiar with key research direction, not only in processing in memory, but you also will have the opportunity to learn about many other things that we are doing in the group. And finally, you're also going to improve your technical, your skills for technical presentation, because you are going to develop one project, and when you finish your project, you will present your work in front of the entire group to get feedback and to figure out ways of extending your work and improving it. So key goal of this course is to learn how to overcome the data movement bottleneck that we have already introduced in the previous slides by programming, benchmarking, and exploring different designs of the processing in memory computing paradigm. There are not many prerequisites of this course, but it's important, and I would say necessary, to be familiar with digital design and computer architecture. You have probably taken the Digital Design and Computer Architecture course from Professor Mutlu. If you don't, you must have probably taken a similar course. But anyway, if you want to brush up, you want to refresh all your knowledge on digital design and computer architecture, you can see in this slide a couple of links to the Spring 22 edition of the course of the Digital Design and Computer Architecture course, and also to the Spring 2023 edition that just started in this spring semester. It's also desirable that you're familiar with C and C++ programming. That's important for using simulators, analyzing workloads, programming PIM architectures, and also desirable if you have some experience with FPGA implementation or GPU programming. That can make things easier and make the experience even more profitable, because you will be able to make progress much faster. But most important thing is that you are interested in future computing architectures and computing paradigms. You are interested in discovering why things work or do not work and solving problems. So you have sort of researchery mindset. And you're also interested in making systems more efficient and usable. So let me talk briefly about the instructors in this course and about the Safari Research Group. This slide is about Professor Mutlu. He is a full professor at the DITET department at ETH Zurich. He joined ETH in 2015, and he has very large experience in teaching and research in computer architecture, computing systems, hardware security, bioinformatics, etc. The rest of us is me, Juan Gómez Luna. I am the lead supervisor in this course. I will be delivering most of the lectures, but we will have also a participation of other people, like, for example, Geraldo, Konstantinos, and Nika. They are going to teach lectures. They are going to also supervise the students taking this course, and they are PhD students of this group working on processing in memory, near data processing architectures, and related topics. So. You are free to contact us if you want to learn more about us, about the research that we are doing. But first of all, you can maybe take a look at the website of the Safari Research Group. This is a very large group, around 40 people these days. Here you can see a relatively old picture of many of us, and well, we are very active in research and in teaching in general, as you may know, and we also are trying to disseminate our work as much as possible. One of the ways of doing so are the Safari newsletters that we publish from time to time. This link here, it's to a relatively old edition of the Safari newsletter, but we are right now preparing a new newsletter that I think it will be published very, very soon. We also do many other research activities, for example, Safari Live seminars that are like, let's say, long talks or seminars where we cover in detail one specific topic, as you can see here for these different screenshots of the different talks. Some people from our group, also some external researchers as well, talking about the research. Overall, very, very interesting seminars. Here you can find a link to our website where you'll find the next, well, past and also upcoming Safari Live seminars. The next one will be delivered by Dr. Haiyu Mao, who is a postdoc in our group. She's going to talk about GenPIP, which is by the way, processing in memory proposal to accelerate genome analysis. So as soon as we know the exact date for this Safari Live seminar, we will announce it and invite everyone to join. And the Safari Research Group, as I said earlier, we we focus on many different areas of computer architecture research, computing systems, hardware, software co-design, bioinformatics, etc. And as you can see in this list, in this slide, all parts of computer architecture, from memory and storage, heterogeneous and parallel systems, system architecture and interaction, energy efficiency, fault tolerance, hardware security, and many, many more things. So let me know if you have any questions so far. I'm also keeping an eye on the YouTube chat in case that there are any questions in YouTube. Okay, so course requirements and expectations for this processing in memory course. Attending is required for all meetings. You're going to have anyway a lot of flexibility in that sense because the meetings are recorded, so they will be available in YouTube for you to watch them whenever you have time. You can also rewatch them if you didn't get something and want to give it another try, or if you are super interested in a topic, you will have also a good chance to go deeper into any of the contents. Study the learning materials, those materials that we are recommending. We will talk about some of them in a few slides. Each of you are going to carry out a hands-on project. We are going to discuss these projects in an upcoming meeting, and there you will do your own work, you will implement your own design, or you will do your own analysis of workloads, and you are going to be in close engagement with your supervisor or supervisors. We expect that you participate, you ask questions, contribute, so try to be proactive with your thoughts and ideas, and also read relevant papers. I think you have a very good opportunity to learn a lot about an important trend in computer architecture these days, processing in memory. And I would really like to encourage you to take advantage of this course as much as you can. At the same time, also encourage you to do good work with your research project, because we are going to help you a lot. And if it's your work is really good, we may even try to publish it, which would be really ideal and very, very useful for your career as well. We provide a lot of information in this course. The central point of synchronization is the course website. You can find a link there in this slide. There you will find useful information about the course, but also check announcements in Moodle or announcements that we will make over email. And whenever you have any questions, don't hesitate to use the Q&A forum that we have in Moodle. We will try to reply as soon as possible. Yeah, this is again about the course website. On the right-hand side, you can see a screenshot of this course website and the link to the website of the Spring 2023 edition. And in the same slide, you can also see a link to the playlist in YouTube where this current lecture will be, but also all the upcoming lectures that we are going to have, one every Thursday at 9 a.m. Zurich time. For the first meeting, I already sent you over email some recommended materials. Well, recommended, required. I think that's not so important at this point. I would definitely recommend you, and that's why they are considered required materials. I would definitely recommend you to read the first one, this book chapter titled A Modern Primer on Processing in Memory, because it's a very detailed summary of the main trends in processing in memory and some important research works, many of them or most of them from our group that are, I would say, the state of the art in the processing in memory research. But I can also recommend you many of our lectures and talks on processing in memory. A really good one is this one on memory-centric computing that Professor Mutlu has delivered several times. This link in particular corresponds to a lecture in October 2021. By the way, sorry. By the way, this afternoon at 4 p.m., I will also be delivering similar lecture on memory-centric computing as part of the seminar in computer architecture that we also have this semester. And here you can see a few more recommended materials, and there's also article, a paper about processing in memory, a workload-driven perspective, a couple more lectures from Professor Mudlu, and also here this link to the paper about our seminal work on the admin PIM architecture, but also several links to videos, slides, and etc. So all of these recommended materials. In meeting 2, as I already said before, we are going to announce the projects and we are going to give you a description about them so that you have the chance to select what's the project that you want to carry out over this entire semester. And after that, you will start working, first of all, probably reading some papers or materials that your supervisors will provide, and then you will have one-to-one meetings with your supervisors pretty frequently, let's say once every week, in order to update them about the progress of your project, get feedback, etc. It's important that you study the learning materials that your supervisors provide, and for the next meeting, I would definitely recommend you to watch the memory-centric lecture from Professor Mutlu and read the Modern Primer book chapter, because that's going to give you a pretty wide overview of the processing in memory and memory-centric and data-centric computing systems, and probably will help you understand what are the projects, the topics of the projects that we will present next week, and based on that, make the right decision based on your interests. So in the next meetings, as I said, we will present the we will present the different potential projects, but later meetings as well, we will have lectures on real PIM architectures, PIM programming, and also recent research works from our group. You will have individual meetings with your mentors, and at the end of the semester, you will present your final project in front of our group. Anyway, if you want to have a whole view of the processing in memory course, of the different contents that we are going to cover over the semester, etc., you can already take a look at the website of the fall 2022 edition. As you see, there were in total, I think, 16 lectures. You can take a look at them if you want, and also some more learning materials that are there. So let me know if you have any question at this point. If you don't, what I'm going to do in a few more minutes is to give you an introduction to processing in memory and memory-centric computing in order to motivate a little bit more about this course, and also give you a brief description of what are key trends in processing in memory, so that in our next meeting you are much more on track, and the rest of the meetings, hopefully the upcoming lectures, hopefully will be even more profitable. So, as I said earlier, the access to data is critical in current computing systems these days, and this affects all sorts of systems, from CPUs, FPGAs, GPUs. There is a big issue with going to main memory or even going to the storage, which can be even worse, and bring data to the processing unit. A lot of execution cycles and a lot of energy is spent on doing so, and even though there have been many attempts to overcome these data movement bottleneck, still is a big issue in current computing systems. And that happens even though, if you look closely to a real processor these days, a conventional processor such as a CPU or a GPU, you will see that many of the resources, a lot of their die area is already spent on trying to improve the access to data. You can take a look at this simplified representation of a multi-core CPU with 9 cores that are these red blocks that you see, but the rest of everything that you can see in the figure, all these green blocks and the yellow ones correspond to memories, on-chip memories, and also memory controllers to access off-chip memory and storage, as you can see. So even though most of the computing system is devoted to memory and is devoted to storing data, memory is still a big issue in current computing systems. And there are three key system strengths. The first one is the data access. It is a major bottleneck because applications are increasingly data hungry these days. Energy consumption is a key limiter, and data movement energy dominates compute. And this is especially true for off-chip to on-chip data movement. And the reason why this has happened is because over the years, over the last several decades, we have seen the processing part, the compute elements of the processor to improve, to increase their performance much faster following Moore's law than what memory has done. Moore's law, as you may remember, we have seen the performance of processors doubling every 18 months or every 2 years or so. But unfortunately, that is not what has happened in memory. Here in this figure, in this in this plot, you can see how much the capacity, bandwidth, and latency in memory, in DRAM memory, has improved over the last 20-something years. And as you see, the improvements have not been so fast as they have been for processors, for the computing elements themselves. We see that the memory latency is probably the one of these three characteristics that has improved more slowly, but also bandwidth has increased quite a little amount if you compare to the improvement of the processing elements themselves. And this affects many different workloads these days. Here you can see some examples, but there are many more workloads. Here you see databases, graph and tree processing, data analytics, data center workloads, but we can add machine learning, genomics, and many, many more works. So long memory access latency and low memory access bandwidth cause a performance bottleneck and also cause an energy bottleneck. We can take again another look at this picture of the energy perspective, how communication dominates arithmetic, because computing floating point double precision addition is way less energy consumption than accessing data from memory. As we said earlier, between 2 and 3 orders of magnitude more energy consumption from accessing data than from operating on that data. And it's the energy, and it's against the performance perspective. If you look at the CPU or a GPU these days, you'll see that most of the execution cycles are spent on accessing data from off-chip memories, from the external DRAM memory. This slide comes from Professor Mudlu's PhD thesis when he designed and implemented the run-ahead execution engine. And for motivation, he observed that around 55% of the execution cycles were spent on accessing DRAM due to L2 misses in the CPU. And this slide is already old, it's from 2003, but more recent one, this one, for example, a NISCA paper from 2015, where Google showed that most of their data center workloads were heavily burdened by the access to the data. This analysis here follows the top-down approach. That is a way of characterizing how the execution cycles in the pipeline are being spent. And one thing that they observed is that a majority of those execution cycles, a majority of the pipeline stalls that were wasted, let's say, in the processors, were due to access to data mainly from the off-chip memory. So the problem is that data access is a major performance and energy bottleneck, and one reason for that is that the current design principles cause a great energy waste and a great performance loss. The reason or the problem is that processing of data is performed far away from where the data resides. And that happens because current computing systems keep using this von Neumann model, where the compute unit and the memory units are separated and connected by a communication unit. If this communication unit is not wide enough, this communication unit is just a narrow memory bus, then this communication is going to become a bottleneck because the communication unit behaves like a funnel. So that's basically what happens in current computing systems these days, and this affects the access to data in the main memory and also the access to data in the storage. So the result is that a lot of execution cycles and a lot of joules are spent on accessing data from the storage and from the memory. So today we have grossly imbalanced systems because processing is done only in one place. We call these systems processor-centric systems. And in these processor-centric systems, data moves a lot, and this is energy inefficient, is low performance, and is complex. And the ways of trying to alleviate all these data movement have also been complex and have made that processors and accelerators are bloated. They have complex hierarchies, deep cache hierarchies, complex mechanisms, such as different types of prefetchers, but still the processor-centric systems tend to be energy inefficient, low performance, and complex. And all of that is because all these data movement that exist between different components in the system, not only from the DRAM to the processor itself or the system on a chip here, but also between all the components of the system on a chip. So the idea here, the key idea here, and the main goal of this course is to make compute systems more data-centric, and one way of doing so is processing in memory, which proposes to compute where the data resides or where it makes sense. A value that or some figure that I already mentioned earlier, 62.7% of the total system energy is spent on data movement in consumer devices. And this is just one example analysis from 2018, but there are more recent works showing the same or even worse trend in terms of energy consumption due to the data movement. So we need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, and make computing systems more data-centric or more memory-centric. And these days we have a good opportunity. The reason is that all different issues in scaling memory have encouraged academic researchers and industry to push for new approaches, new innovations to make the access to data faster, more energy efficient, and in summary, better and improve computing systems. And some of these innovations are, for example, non-volatile memories. We will talk about them in this course for sure, but also other types of memories like 3D stack memories, such as the hybrid memory cube from Micron, or the high bandwidth memory that I already mentioned in the beginning of this lecture. It's the idea of stacking multiple layers of DRAM on top of each other, and at the bottom also a logic layer with some sort of buffers or memory controllers to access data in the DRAM layers at high bandwidth and low latency. And the idea of, or the good point of having this logic layer at the bottom is that we can take advantage of some area, some space in this logic layer to embed compute elements. And that's what many PIM proposals have done until now. Those are the proposals that we call processing near memory. as we are going to see in a few slides. So we have a challenge and opportunity for the future, and we can make compute systems higher performance and more energy efficient. The basic idea of processing in memory is pretty simple, is to provide memory with some sort of compute capability, and then from the host processor, from the CPU or the GPU, offload some computation to the memory side, to the processing elements or whatever compute capability that the memory may have. That computation will be done near the memory, and then the results return to the processor. But to enable this new paradigm, it's necessary to tackle and design many different components of the system in a different way. We need compute capable memory and controllers. We also have to probably modify part of the design of the processor chip, improve and create new hardware and software interfaces, same as software and languages, probably modify and adapt algorithms to the new system. And all of these changes span multiple levels of the computing stack, from the algorithm to the devices. There are many ways of doing processing in memory, also called near data processing. The key idea, as I said, is to move computation closer to where the data reside, but there are different ways of doing so. And here you can see some examples, for example, taking advantage of the logic layer in 3D stack DRAM, or placing some sort of compute element near the or inside the memory controller of the CPU, or maybe even on the DIMM itself. Remember the AXDIMM proposal from Samsung that I mentioned in the beginning of the talk. Here you see one example of real PIM architecture is the UPMEM PIM architecture. Remember here, the UPMEM are placing small processors inside the DRAM chips near the memory arrays, but also, and the other possibility that I just mentioned, placing these processing elements on the DIMM, in this case, a reconfigurable fabric. And there might be different possible designs for the processors themselves, the compute capability itself, like fixed function units or reconfigurable architectures, such as those in AXDIMM or general purpose programmable cores. This is the case of UPMEM, for example, but also the possibility of doing computation with the memory itself. This trend is what we call processing using memory, and we are going to introduce it briefly in this lecture. So there are different ways of doing processing in memory, different approaches, but in general, we can classify all these approaches into two main types, or two main PIM approaches that we call processing using memory and processing near memory. We are going to introduce them in the remaining part of this lecture. This table, by the way, comes from the book chapter that I mentioned in the beginning of this meeting, of this lecture, is Modern Primer on Processing in Memory, that you can access from this link. But now let's take a quick look at the two possible approaches in processing in memory. And yeah, I think that we are going to set the stage for later lectures. So I hope that you'll find this brief introduction interesting. The first one of these two approaches is what we call processing using memory. And the idea here is to, by changing memory chips minimally, perform computation using the memory cells or the memory components themselves. These approaches take advantage of the analog operation of DRAM cells and DRAM components or other sort of memories, but for now we are going to focus in DRAM. One thing that different researchers and especially researchers in our group realize is that by making small changes to the way that DRAM operates, it's possible to perform both data movement and computation, and this way exploit the large internal bandwidth of DRAM memory by exploiting the analog computation capability. There are multiple examples of this direction, of this trend, and you can find some links in this slide. I'm going to talk about two of them. The first one is called row clone. This was an idea proposed in 2013 by Vivek Seshadri, one PhD student of Professor Mutlu in the Safari Research Group. And with this row clone technique, it's possible to do very fast and very energy efficient in-memory copy and initialization. And even though in your programs, when you're coding, you are not doing copy and initialization all the time, but these two operations are extremely important for computing systems. There are key systems and operating system operations that require data copy and initialization. And in fact, in a relatively recent work from Google, they observed that 5% of the cycles in Google's data centers were spent on moving data, either with memmove or with memcopy. And how is the way that current computing systems move this data? The only thing that they can do if you want to perform a bulk copy operation from one part of the memory to another part of the memory is bring all this memory chunk by chunk or cache line by cache line to the processor all the way up through the cache hierarchy, performing a copy operation in this cache hierarchy in the L1 and then write it back to the memory. And this is an operation that takes high latency. It consumes a lot of bandwidth in this memory channel, which is also creating contention with other applications or with other operations in the same process or the same application, and also causes cache pollution. And in summary, unwanted data movement. And this is costly in terms of latency and in terms of energy consumption, as you can see. This is just an example for a 4 kilobyte page copy via DMA. In future systems, and thanks to ideas like row clone, it will be possible to perform a bulk copy operation as simple as that, directly copying from one part of the memory to another part of the memory. And this can be done with low latency, low bandwidth utilization, no cache pollution, and no unwanted data movement. And for a comparison, you can see that basically latency and energy consumption can be reduced by 2 orders of magnitude. Doing this inside a DRAM subarray can be extremely simple if properly enabled by simply activating 2 rows in a consecutive way. First of all, we activate the source row, row A, then we transfer this row to the local row buffer, to the sense amplifiers when we activate these sense amplifiers, and then with a second activate to another row, we can copy everything we have in the row buffer to the destination row. This just with 2 consecutive activates and at a negligible hardware cost. This is one of the techniques that the row clone paper presents, and as you can see is extremely positive results, like 11.6 times shorter latency and 74 times lower energy consumption with respect to the baseline that performs the bulk copy operation all the way through the cache hierarchy and the CPU. This is the paper. Here you can find a link to slides, presentations, etc. And even though this idea of row clone might sound like too futuristic or maybe something that is not easily realizable in real systems, the truth is that some researchers just 3 years ago showed that it's even possible to do this sort of bulk copy operation inside DRAM using off-the-shelf DRAM chips. This is the Compute DRAM paper presented in Micro 2019. That is a very good work and very much recommended reading. Following similar operation principles, also taking advantage of the analog operations of DRAM cells, is also possible to perform bulk bitwise operations, to perform operations such as AND, OR, NOT, majority operations, bitwise operations that can be useful to implement more complex computations such as arithmetic addition, arithmetic multiplication, etc. We are going to introduce these ideas right now, and we will talk in more detail in a later lecture. And all of this at low cost and using the analog computation capability of DRAM. The idea of this proposal that is called AMBIT and was presented in Micro 2017 and is also part of Vivek's PhD thesis. The key idea here is to activate multiple rows at the same time and this way perform computation. We are going to see how. And we are going to see how this can provide extremely good improvements in terms of performance and energy efficiency. You can check all the details in the AMBIT paper. But let me very briefly explain you this key idea of the triple row activation and this key idea of the AMBIT proposal. Imagine that we have 3 rows in DRAM inside the same subarray, and these rows are A, B, and C. Here, for this example, we are going to focus just on one bit line. So in 3 different cells connected to the same bit line, these 3 different cells in 3 different DRAM rows. And as you can see, 2 of the cells are charged, fully charged, and the 3rd cell is fully discharged. The basic idea is that instead of activating each of the rows individually and only a single row, as we normally do when we want to read or write to DRAM, what we are going to do here is activating the 3 rows at the same time. So that means that we activate the access transistor, we close this switch, as you see, and what happens next is that the 3 rows start sharing their charge with the bit line, and that causes a perturbation in the bit line. When we enable the sense amplifiers, when we activate the sense amplifier, this perturbation is amplified. And then the bit line will go to whatever voltage, either 0 or VDD, depending on what was the perturbation on the bit line. But what was the perturbation on the bit line? Well, that depends on what was the charge of the 3 cells that were activated at the same time. And remember, the 3 cells, 2 of them were charged and 1 of them was fully discharged. So what happens is that the most relevant perturbation in the bit line is the charge 1. So the bit line tends to go from half VDD in this initial situation to after applying the perturbation to VDD when we activate the sense amplifier. So this operation that you have just seen on the slide is a majority function. Majority because basically you have 3 inputs, you have 2 ones and 1 0, and the majority of the 2 possible values is 1, so the result is 1. So this is majority. And with the majority operation, we can either obtain and or operations. That's that only depends on what's the value of this Z. If C is 1, then the result will be an OR operation. If C is 0, the result will be an AND operation. So by using majority, we can create an OR inside DRAM and using these analog operational principles. Here you can see an example of how to do AND with 2 rows, A and B, and store the result in a 3rd row, C. What the AMBIT paper proposes is that we have certain rows that are reserved for computation, because observe that here we need a row decoder that is able to activate 3 rows at the same time, and because providing with this capability to the entire row decoder for each DRAM subarray can be very costly, because that makes the row decoder design more complicated. What the AMBIT paper proposes is to have a small row decoder that can activate 3 rows, and these 3 rows are going to be called compute rows or designated rows, D1, D2, and D3 in this slide. So the idea would be to copy the, using row clone as well, the previous proposal, copy from one source row to one designated row, the row A, row B to another designated row, and then row clone a row that is full of zeros to the 3rd designated row, in order to implement an AND. Because remember, in the majority operation, if one of the 3 inputs is 0, the result will be an AND. Then we activate the 3 rows at the same time. We obtain the result of the majority operation or the AND operation in this case, and then we can store the result in the destination row C. You can check the details of this technique in this IEEE CAL paper that was published first in 2015 and later in the micro paper in 2017. Observe that we have just talked about AND and OR and also majority, but if you really want to have a functionally complete set of logic operations that enables you to create more complex operations, we also need NOT. And that's not so easy. What the AMBIT paper proposed was to include 1 or 2 rows in each subarray that instead of having conventional DRAM cells, they have these so-called dual contact cells. As you see, here we have the capacitor, here we have the access transistor, but instead of having just one access transistor that connects the capacitor to the bit line, here there is a second access transistor that connects the capacitor to the bit line bar, to the other side of the sense amplifier. Because the sense amplifier are basically these two coupled inverters, we can have on this side of the sense amplifier the negated value that we have in the bit line, and by enabling this N word line, it's possible to copy one negated value to the capacitor and this way enable the NOT operation. And here in this slide, you can see a step-by-step operation of how to perform NOT using the dual contact cells. The AMBIT paper resulted in a very interesting performance improvements for bitwise operations. And this plot, you see the throughput comparison of a couple of versions of AMBIT to processing in memory based on HMC memory, but also comparison to CPU and GPU. And we basically see something between 2 and 3 orders of magnitude performance improvement. Also extremely good energy savings, tens of times in energy savings compared to baseline system. And the AMBIT paper also shows how this AMBIT technique can be applied to real-world applications such as this bitmap index. You can see more than 6 times performance improvement, so 6 times reduction in the execution time when using AMBIT for this bitmap index, and a few more applications that you can find in the AMBIT paper, and quite interesting improvements in performance and energy efficiency for these different applications. As you see, AMBIT can enable much more, because if you have a functionally complete set of AND, OR, and NOT, it's possible to implement more complex operations. And that's what we proposed in this SIMDRAM paper that was presented in 2021 and proposes a framework for bit serial CMD processing using DRAM. We will have a specific lecture about this SIMDRAM framework, and you can learn in much more detail. So this is the first part of the, let's say, introduction to processing in memory, the first of the 2 directions, processing using memory. But there is another direction that is even more, I mean, it's even more real these days, because there are already some real architectures as the ones that we are going to present in later lectures. And this second trend or second approach is called processing near memory. In this case, the basic idea is to place small processors, small SIMD units, or small specialized function units near the memory arrays in order to have higher bandwidth and lower latency to access the data. Some of these ideas have, some of these proposals have used 3-stack memories. As I said earlier, one advantage of 3-stack memories is that they stack multiple layers of DRAM, but they also have a base logic layer that is CMOS, so it's easier to integrate processing elements in that CMOS-based logic layer, and that's one potential way of doing processing near memory. In that sense, well, this is the example of the hybrid memory cube that I was just mentioning, the memory layers stacked on top of each other and the logic layer at the bottom. Similar design, this is for HMC, hybrid memory cube, but similar design also applies to HBM memory. And yeah, using this example of the 3D stack memory, I want to give a brief overview of a couple of interesting proposals, in this case targeted at a specific domain of applications or domain of algorithms that suffer a lot from the data movement bottleneck, suffer a lot from accessing data from memory, and we can consider them highly memory bound. This application domain is graph processing, and graphs are extremely important these days. They are everywhere, as you can see in social media, for example. They are very useful in social media to see how different users are connected to each other. But performing graph processing on conventional processor-centric systems is challenging and is low performance, and it consumes a lot of energy. And one key reason is that these workloads are so much memory bound that different cores, different threads running on different cores, either in CPU or in GPU, they contend when accessing memory, and the performance cannot scale even if we increase the number of processing elements. You can see on the slide one example, when moving from or increasing the number of cores from 32 to 128, we only see, it's 4 times more cores, we only see 42% performance improvement. And that's something that happens in many graph processing workloads. For example, in the PageRank algorithm, where we have to go over all vertices and we need to update what are the ranks of the successors, of the neighbors of each of the vertices, just with a simple operation, one multiplication and one addition. But the problem with doing that operation is that we need to access very sparse areas of the memory when going to where the neighbors reside, and that causes frequent random memory accesses and very little amount of computation, as you can see, because not much computation is needed to update the RAM. So how to deal with this data movement bottleneck in these sort of workloads? There might be many different ways, but here we are going to quickly review 2 possible ways of doing so. One of them is a 3D stack memory-based accelerator, coarse grain accelerator for graph processing, and the other one proposes some minimal processing in memory support that doesn't change the system so much, but it still can provide significant benefits. So let's first take a look at the coarse grain accelerator. In NISCA 2015, this work Tesseract and in-memory accelerator for graph processing was presented. And the Tesseract accelerator basically consists of 3D stack memory cubes, each of them with their logic layer. All these 3D stack cubes are connected in a network, as you can see in the left-hand side of this slide, and the graph itself, the adjacency matrix of the graph, is laid out over all these different memory cubes, as you see. If we take a look at each of the cubes in the logic layer, of each of these 3D stack memory cubes, we are going to find a crossbar network, and connected to this crossbar network that allows them to communicate and also access data in the memory layers. Connected to this network, we can find all these in-order cores, in-order processors, small cores that can either access memory or communicate through the network interface to the other processors, to the other cores in the same logic die, as you see. So by using this sort of coarse grain accelerator for graph processing, is possible to greatly accelerate graph processing workloads and also do it in a very efficient manner. These in-order cores can communicate and offload computation to other cores, and at the same time can prefetch data in order to bring it to these prefetch buffers that you can see here, and make the access much faster. Basically, you can find all the details about this accelerator in the paper, but we are going to take a very quick look at the evaluation. The authors compared out of order cores processor-centric system with an out-of-order cores and DDR3 memory, out-of-order cores with HMC memory, with the 3D stack memory itself, also a proposal that places computation in the memory controller, and finally the Tesseract accelerator itself. So as you see, with respect to the baseline out-of-order processors with DDR3 memory, the performance is really good, more than 13 times performance improvement for the full-blown Tesseract system with a couple of different prefetchers that really alleviate a lot the access to data, reduce the latency of access a lot, and as you see, resulting in very good performance improvement, same as very interesting energy savings, more than 8 times energy reduction. You can check, as I said, all the details in the paper and the related presentation. And that was one of the approaches to solving the data movement bottleneck using 3D stack PIM memory, 3D stack memory or PIM based on 3D stack memory. The other approach is to provide minimal processing in memory support. And that this work is called PIM enabled instructions that was also presented in SK 2015. You already know the PageRank algorithm that I mentioned earlier. Remember that the problem with the PageRank algorithm is that there is very little amount of computation, but very much random memory accesses. So that causes the data movement bottleneck. And in the conventional architecture, we can see this example. If we want to update the rank of a successor, we'll have to go to main memory, bring one cache line to the host processor, update the rank, and then write it back to the main memory. And this requires to bring an entire cache line, so 64 bytes to the host processor, update maybe 8 bytes, maybe 16 bytes or something like that, or of the entire cache line, and then write it back to the main memory. So this is costly in terms of cycles and in terms of energy. The PIM-enabled instructions paper proposes to use these PIM-enabled instructions that are specialized instructions, such as this PIM add, that what basically do when the processor reaches to this instruction, what it basically does is calling the corresponding processing element near the memory, sending it one value to update the rank, and performing the operation inside the memory or near the memory. And that saves a lot of data movement, because instead of bringing 64 bytes and then writing back 64 bytes, we can just send 8 bytes, the value that we need to add to the main memory, and that's it. So that's the basic idea in PEI. The authors tested the PEI idea with different workloads from graph processing, but also other benchmarks from data analytics, machine learning, and data mining, etc. And this is the summary of the PIM-enabled instructions that they supported in their proposal, the ones that they tested in their work, which doesn't mean that these are the only possible ones. You can come up with your own PIM-enabled instructions if you wish, depending on your on the specific application or the specific domain of applications that you are targeting. Important thing as well is to make an intelligent decision when it comes to offloading computation to memory or not. And this is, by the way, one important topic that we will cover at some point in this course as well. It's important to keep caches coherent and to do offloading only whenever it's going to be beneficial. Because what happens if you need to update contents of a cache line that already resides in the cache hierarchy because it was previously accessed by your program, by your application? Well, in that case, you probably don't want to offload anything to the memory side, and you want to just update that cache line in the host processor because the data is already in the host processor. And actually, it might even be a dirty cache line, and a dirty cache line is updated here in the cache hierarchy but not in the DRAM memory. So the intelligent decision here would be to perform the updates in the host processor. And that's why the PEI paper proposes this locality monitor that can check what are the contents of the last level cache, see if one specific cache line that we want to operate on is in the cache hierarchy or not. If it's in the cache hierarchy, then we are going to operate on it in the host processor itself. If not, we will offload the computation to the memory side, to these PCUs that are near each of these DRAM controllers and have direct access to the data in the different DRAM layers of the 3-stack memory. By exploiting these PIM-enabled instructions and this locality-aware execution, this intelligent scheduling, it's possible to save significant amount of execution cycles. You can see here around 50% or almost 50% performance improvement over the baseline, the CPU only baseline, and also some interesting energy savings, up to 25% energy savings for the different workloads that were tested in the PEI work. Here you can find the links to the paper and the presentations, and is for sure very much recommended reading. So this is basically the introduction to the two main directions in processing in memory. We are going to keep talking about these two main directions, but from now on, we will focus more on specific examples of processing near memory systems. We are going to talk a lot about real processing in memory systems, processing near memory systems, such as the UPMEM PIM architecture or the proposals from Samsung or SK Hynix that I introduced in the beginning of the lecture. But we will also have some more lectures about processing using memory. So you're going to get a very nice view or overview of the entire spectrum of processing in memory techniques. We will also talk in this course about more things that need to be done at different levels of the system, of the computing stack, to enable the adoption of processing in memory, and these different actions that we need to perform to enable the adoption of processing in memory span, as I said, multiple levels of the stack, from applications and software, from compilers and interfaces for programming. It's important to keep in mind as well coherence, synchronization, virtual memory, and also security issues such as isolation and many more, and also runtime and compilation systems that allow us to do adaptive scheduling and intelligent offloading, as what we have just discussed for the PEI paper. And of course, we also need infrastructures to assess the benefits and feasibility. And that means benchmark suites, that means simulators, prototypes, etc. But all of these can be achieved, can be solved with a change of mindset. And this change of mindset needs us to requires us to revisit the entire computing stack. We talk about we talk about the approaches to processing in memory, many recent research proposals, and also what needs to be done to enable processing in memory in our book chapter, A Modern Primer on Processing in Memory. Here you can see the abstract of this book chapter, and here the table of contents. As I said, this is a very very much recommended reading, I would say a required reading to be successful in this course from the very beginning. And yeah, for sure, I think you're going to enjoy it as well and learn a lot about this exciting trend in computer architecture. So this is all from my side for today. Now, if you have any question, please let me know. I don't see any question in YouTube. I hope that everyone attending the lecture enjoyed it, and I hope that everyone will be also watching the next lecture next Thursday. Is there any question in Zoom?
No, it's all right. Thank you.
Okay, thank you very much.
Have a nice day.
Yeah, you too. If there are no questions, I think we are done for today. I will be glad to continue with this processing in memory course next Thursday.
All right, bye.